Greetings to you, learners. I welcome you to another learning time via this channel. Kindly pay full attention as I take you through the lesson in this video. And let me say that if you have questions, you need clarifications, please type those in the comment section. And after the video, if you learn from it, kindly give it a like, recommend to your colleagues within and outside your university. Also click on the subscribe button so that you will be the first to receive the latest on this channel. Let's delve into the content I have for you in this video. Well, you are familiar with the different types of motion. These are basic knowledge from your O-level days. You have random or irregular motion. You have what is called the linear motion or translational. Then you have oscillatory or periodic motion. And we have rotational, circular motion. Random irregular motion, no definite path. Paths cannot be predicted. That's why I said it to be irregular. Then translational or linear, that can be predicted. However, the body or the motion is in a straight line. A straight line. For oscillatory or periodic, it is a type of motion where the body passes through a common point at a regular interval. Back and forth type of motion. And for example, from secondary school, you know the simple harmonic motion. That's a typical example of oscillatory motion or periodic motion. And we have rotational or circular motion. And this is a body following a curved path or a circular path. For example, a disc spinning on its axis, that's a body, a circular motion. A ball spinning in its axis is also a body circular motion. But at times, you may have an object or a body that is experiencing both rotational and also translational motion. For example, you kick a ball on the grass, the field, from a point on the field to another, maybe from the center point towards one of the goalposts. As the ball travels straight line, then it also spins. So at that point, the ball is experiencing two types of motion, which is translational, that is moving from where you kick it to where you want it to go, that's the goalpost, and also spinning on its axis as it travels from where you kick it at the center of the field towards the goalpost. So we'll be dealing more on rotational or circular motion. But I need to also bring you up to speed on the common terminologies used in translational motion or linear motion, which will help in also understanding the terminologies used in describing bodies undergoing rotational or circular motion. You are familiar with distance or displacement. Distance, displacement, distance is scalar, displacement is vector quantity. But it's just about the length of space between two positions, and it's measured in meters. The standard national unit, SI unit, is meters. Then you have what is called the speed or velocity. linear speed, linear velocity. Also, speed is scalar, velocity is vector, and is measured in meter per second. Then you have the acceleration, which is the rate of increase in linear velocity with time. It's measured in meter per second squared. Then you have momentum, that is the product of the mass of your body and its velocity. Also, we have the force, which is the physical influence that tends to change the position of an object. For example, the ball kicked from the center of the field to a goalpost. The kicking is the application of the force. And it has a mass, then you give it the velocity. So the motion, such a ball will have momentum as it moves. And the change of position of that ball is due to that physical influence, which is the kick, which is a form of force applied on the object, which in this case is the ball. But in rotational motion, instead of having linear distance or displacement, linear velocity, linear acceleration, and so on and so forth, we now have what's called angular displacement. Angular displacement, then you have the angular velocity, you have the angular acceleration, you have the angular momentum, and we have what is called the torque. We're still going to dwell more on the angular momentum and the torque in another video. So angular displacement represented as theta or delta theta, change in theta. It is the angular change of position or change in the angular position of a body. For example, if you look at the diagram on the right hand side of your screen, the blue circle is the part of the object represented by that black dot. If that dot, by the application of a force, moves from the point it is to the point Q, you can measure the length traveled on that curve, which in this case is S, that we refer to, or that used to represent linear displacement or distance. And the angle now swept as that dot, that object, traveled a circular path, the equivalent angle swept by covering the distance x, the equivalent angle swept by the black object traveling that circular path is called theta, which is the angular displacement. And the point where the dot is will be marked as theta subscript 1, that is the initial position of the object, the black dot, and Q will be marked as theta 2. So the differences between the two theta value is your change in the angular position, which is theta. And theta is related to S. There is a relationship between the angular displacement and the linear displacement. And you can see, I didn't just put the relationship there, I show you how they got that. From the figure, if you check very well, you know your Pythagoras? Right angle triangle, if you check, it's like right angle triangle. Tan theta will be S opposite over R adjacent. R is like the radius of the circular part. And for very small angle, you know that tan theta is approximately equal to theta. So very small angle, tan theta will be S over R. And since for small angle, tan theta is equal to theta, that means theta is equal to S over R. S over R. We have S over R here. And from there, S is equal to R theta. That is, if I know the angular displacement and I know the radius of the circular part that an object is following, then the product of the two will give me the equivalent distance covered by the object if the object were to be moving in a straight line. That's it. So you can see what S stands for. The distance covered by body object, no circular part. R is the radius of the circular part. Both the unit are meters. Then theta is the angular displacement, which is measured in radian. The angular velocity, it is the rate of change of angular displacement. Rate of change of angular displacement. That is d theta over dt. Rate of change of angular displacement. D theta over dt. And that's what we have here. We check what we have here. However, we can also show the relationship between the linear velocity and the angular velocity. From the linear velocity, you know that velocity is rate of change of distance or displacement with time. And recall that S is equal to R theta. We obtained that just now, the previous slide. So substitute where you have S, R theta. And for the body traveling on a path, R will be constant. It is the position that will change. The theta will change. Not R. Theta will change. R is a constant. For a body moving along the curved path, per time, the position changes. Theta changes. So R is a constant. Then you have d theta dt. And if, for the definition, if omega is equal to dt, if from the definition, if omega is equal to dt, the theta rather, dt, then you can have your theta equal to omega dt. And if you integrate that, we have omega t. And if you check the last part, that's what we have here. Theta is equal to omega t. So where you have omega t, you have your theta. Put omega t there. So you have r d omega t dt. And if you differentiate the omega t with respect to t, then you have omega. So that means your v is equal to r omega. That is the difference between the linear velocity and the angular velocity. That is, the angular velocity of an object in the circular path or rotating object and the radius of the circular path will give us the equivalent velocity if the body were to be moving in a straight line, which we call the linear velocity. Also, we could see I listed what each of the parameters stands for: omega, v, r, theta, and t, and also the units. Then acceleration too. Angular acceleration, alpha, is equal to increase in angular speed with time is angular velocity with time. That is angular velocity now will be angular acceleration dt. We can also obtain relationship between the linear acceleration and the angular acceleration. And obtain relationship between them. And from the what I'm doing is to build from the base up, from what you know to what you need to know. So for the acceleration, linear acceleration, you have the v dt. And recall that the v is r omega. So substitute r omega, the expression. And because r is constant, the radius of the circular part, what changes is the speed, which is a function of theta, angular speed, which is a function of the angular displacement. You see that? D dt, then omega is theta dt. Then you see that? So you have theta dt omega. Then the omega dt is according to what I have defined earlier. So here you have the omega dt put you have the which is the angular acceleration. So you obtain the relationship between the linear acceleration and the angular acceleration. You can work with it. However, don't also forget that questions may arise whereby you will be given just displacement and angular displacement, and we need to calculate the angular acceleration. That means you, particularly if they are continuous values, at least in terms of t time, continuous, in terms of t time, we need to differentiate. Also, if we given omega, we need to also obtain angular displacement. That's why I said in the first video, the knowledge of differentiation and integration, calculus, is very important in this course. Other ones, we have the angular momentum, which is also related to the linear momentum. And we also have the torque, which is also related to the force. Force is for linear motion, torque is for a body in rotational or circular motion. Linear momentum is for linear motion, angular momentum is for a body in rotational or circular motion. We still delve into that in another video. But this was just part of completing the comparison between linear, translational motion, and rotational motion. So they are just comparing the parameters that we have discussed earlier in the tabular form as a summary. We have the distance, displacement represented as x, and we have the angular displacement represented as theta. Then we have the speed of velocity represented as v, then the angular speed of velocity represented as omega. Then you have acceleration, which is the rate of change of velocity with time. Then we have the angular acceleration, which is also a rate of change of angular velocity with time. And from that equation of acceleration, we obtain the first equation of motion. You know it from secondary school, v equals u plus at. Likewise, equivalent for rotational motion, and obtain it, which is omega subscript f equals to omega subscript I plus alpha t. Now let's compare the two. You see, v is final velocity, wf is final angular velocity, u is initial velocity, the omega subscript I is the initial angular velocity. A is the linear acceleration and alpha is the angular acceleration. Then time t is there. So we just look at it. So if you know that of the for linear motion, then you can easily write out expressions motion of motion for angular or rotational circular motion. You can also derive. I'll show you how it is derived. That's what we have in the box on the right hand side. If you study it, V equals R omega, and also A is equal to R alpha. So we can have your substituting where you have V, that means you have your omega subscript F, then you have your U, you have your R omega subscript I, then plus where you have your A, you have your R alpha, T. You factorize value side by R, then you have the expression omega subscript F equals to omega subscript I plus alpha T. You have other ones too. Again, wherever you have your V, that means you have your omega subscript F, and you have your U, you have your omega subscript I, inertial angular velocity, then you have your linear acceleration, you have your angular acceleration, and you have your T. So if you check for both, that's what you see throughout. For example, look at S, equivalent rotational motion is theta. You see A is alpha, and you see omega subscript I, U, omega subscript F, V. You see that. So you know motion of motion for linear, you can derive rotation. And obtaining this for each, you see it. You want to just study it. Let's see. You can derive the equivalent equation of motion, rotational motion, from that of the linear motion, linear or translational motion. You can obtain equivalent. Straightforward. The next video, we'll be looking at numerical examples where we apply some of the expressions or formulas that we have been exposed to in this video. Again, stay tuned, subscribe to the channel, put up your comments, observations in the comments, and also be a blessing to others by telling them about this lecture video. It gives more time for interaction beyond what you can do in the class. I wish you shining success. See you in our next video. God bless you.